Welcome back, everyone. I'm absolutely thrilled to have you here for another explainer. Today, we've got a fantastic and honestly, a wildly vital topic on the agenda. We're going to completely demystify the alphabet soup of power backup systems that keep our critical infrastructure alive. You know, we hear these acronyms thrown around all the time, UPS, IPS, but understanding the actual architecture beneath them, that's what separates a truly resilient, fail-proof facility from one that's totally vulnerable to the whims of the electrical grid. So we're going to break down exactly how these systems work, why they matter, and most importantly, how to choose the right one.
To really set the stage here, I want you to ask yourself, what actually happens to a massive data center when the power blinks for just 20 milliseconds? Now for you and me, 20 milliseconds is literally faster than the blink of an eye. You wouldn't even see the lights flicker in your living room. But to a highly sensitive MRI machine or a rack of servers processing millions of financial transactions, well, that 20 millisecond gap is an absolute eternity. It can be catastrophic. We're talking corrupted data, rebooting life support systems, or crashing an entire automated assembly line. The stakes here are incredibly high.
Okay, let's dive into this. Here's our roadmap for today. First, we'll look at the power protection dilemma. Second, unpacking the UPS. Third, understanding the IPS. Fourth, a head-to-head power clash. And finally, real-world applications. Section 1. The power protection dilemma. The power coming from the grid isn't always perfectly clean, and that creates a massive vulnerability. Section 2. Unpacking the UPS. Let's look at how we actually solve this problem.
To solve that dilemma, we have to recognize that we're constantly facing power quality issues, sudden surges, dangerous spikes, and voltage sags. And this delicate reality brings us to our first highly sensitive power contender, the uninterruptible power supply. By definition, a UPS provides near instantaneous protection from input power interruptions, using energy stored in its batteries. But actually, scratch that. I want you to think of the UPS not just as a battery in a box, but as an active shield. It's always awake, it's constantly working. While the grid power is fluctuating wildly out there, the UPS is actively filtering, conditioning, and buffering against those surges and sags. It literally stands guard between raw, messy utility power and your perfectly calibrated equipment.
Let's look under the hood at the mechanics, specifically focusing on the gold standard, the online double conversion UPS. This system sequentially scrubs dirty power in such a fascinating way. First up is rectification. It takes the incoming, messy AC power from the wall and converts it into pure DC power. Second is charging, where that DC power is used to constantly top off the internal battery bank. Third is inversion. The system takes that DC power and converts it back into a pristine, regulated AC sine wave to feed your equipment. It's literally double converting the power to clean it. And fourth is the bypass. This is a static switch that safely moves the load back to raw mains power if the UPS's internal components ever suffer a failure, so you never go dark.
And because of that brilliant double conversion process I just described, the transfer time for an online double conversion UPS is exactly 0 milliseconds. Zero. No way, right? But it's true. This is incredibly exciting from an engineering standpoint. Because your equipment is always being fed by the inverter, rather than directly from the wall, there's absolutely no switchover time when the power goes out. The grid fails, the battery just seamlessly keeps feeding the inverter, and your critical load experiences true power isolation. It never even knows a storm is happening outside.
Moving right along to Section 3, understanding the IPS.
Now, while the UPS is a precision instrument, the IPS is built for a totally different kind of endurance. An instant power supply, or IPS, is a high-capacity inverter system paired with large, robust lead-acid batteries. While it's functionally similar to a basic standby UPS, it's generally designed for much longer backup durations and less sensitive loads. If the UPS is an active shield constantly blocking hits, I want you to think of the IPS as a safety net. The IPS relies on the raw mains power for as long as it possibly can, and it only springs into action to catch your equipment once the utility power has actually fallen away.
The flow of electricity here is much simpler. In normal mode, the IPS simply passes the raw mains power straight through to your equipment, while using a built-in charger to top off its massive batteries. It's basically a straight pipe. But in backup mode, when a complete power failure is detected, a mechanical relay physically switches the load over to the inverter. And you know, it's that physical mechanical relay switch that creates a critical difference in performance.
Section 4. The head-to-head power clash. Let's see how these two stack up.
It is time to pit these architectural philosophies against each other in a heavyweight boxing match. Let's see exactly where each system shines and where they fall short. In the UPS corner, you have precise, rapid protection. Transfer time is an undetectable 0 to 8 milliseconds. It offers comprehensive protection against surges, spikes, and electrical noise. But it burns out fast, typically providing only 15 to 60 minutes of battery life to let you safely shut down servers or fire up a backup generator. Over in the IPS corner, you have slower but incredibly long-lasting raw power. The transfer time is a noticeable 20 to 50 milliseconds, and it primarily just provides backup power without all that heavy filtering. But look at that battery life. It can keep the lights on for 2 to 8 hours, or even more.
I really want to isolate this specific metric because it is absolutely vital: the output waveform. A high-end UPS provides a pure sine wave. If you visualize it on an oscilloscope, it's a perfectly smooth, rolling curve of energy. Sensitive electronic components, like medical processors or server power supplies, absolutely require that clean curve to function properly. An IPS, however, often produces a modified or square sine wave. It's blocky, it's stepped, and it's harsh. It's totally fine for spinning a ceiling fan, but it will cause sensitive IT equipment to run hot, buzz, or completely fail over time.
Section 5. Real-world applications. So where do these units physically belong in the real world? Let's map out their ideal habitats. Because of its active shield properties, a UPS is strictly mandatory in high-stakes, critical applications. We're talking about data centers and IT rooms where preventing data loss is everything. We're talking medical facilities, where you literally cannot have an MRI or life support system rebooting during a procedure. It's essential in industrial automation too, protecting programmable logic controllers where even a momentary dip could shut down a multi-million-dollar production line. And of course, telecommunications, where maintaining signal integrity is the whole shebang.
In stark contrast, the IPS is the perfect, cost-effective fit for applications where a brief power blink is completely acceptable. It is the absolute champion of residential backup. If you live in an area with extended rolling blackouts, an IPS will keep your lights, fans, and televisions running for hours on end. It's also perfect for commercial and retail spaces, providing general emergency illumination. Think about it. If the power drops, the lights blink for 50 milliseconds and then come right back on, nobody is harmed and no data is lost.
Let's elevate this discussion to some pro-level engineering specifications. When designing critical infrastructure, you're often going to see the IEC 62043 VFI classification. VFI stands for Voltage and Frequency Independent. This is the technical term confirming that the output power provided to the load is entirely independent of any crazy voltage or frequency fluctuations happening on the input utility grid. It's the absolute gold seal of power conditioning.
Another essential metric you'll spot on elite specs is total harmonic distortion, or THD. High-quality systems must maintain an output THD of less than 3%. Why does this matter? Well, high harmonic distortion generates excessive heat. Keeping that THD under 3% ensures the longevity and physical survival of the highly sensitive capacitors inside your servers and medical devices. Basically, it protects your massive investments from aging prematurely.
And finally, for incredibly harsh environments, think heavy industrial plants, mining operations, or marine applications on massive cargo ships, engineers will utilize galvanic isolation. This involves placing a heavy physical isolation transformer right on the output of the UPS. It provides a necessary, absolute physical barrier of protection for the load against severe common-mode electrical noise and devastating ground faults. It's basically the ultimate defensive wall.
As we wrap up this deep dive into power architecture, I want to leave you with a thought. We've seen how the difference between 0 milliseconds and 20 milliseconds can literally define the line between success and catastrophic failure. So, considering these razor-thin, critical millisecond margins, how vulnerable is your current infrastructure to the very next power blink? I hope this explainer has given you the tools to evaluate your own facility's power protection and sparks your curiosity to investigate your systems even further. Thank you so much for learning with me today, and stay empowered.